Welcome to a video lecture on empirical and molecular formulas. We're going to start by looking at some chemical formulas and trying to understand what the subscripts mean. If you have a chemical formula like HCl, this is hydrochloric acid, and if you have 1 mole of HCl particles, you're often going to have to know how many moles of each element you have. So if we look, we have an understood subscript of 1 in next to both of these elements. So if you have 1 mole of these molecules, then you will have 1 mole of hydrogen atoms and 1 mole of chlorine atoms. If we look at this formula of magnesium hydroxide, and you have 1 mole of these formula unit particles, then you will have, notice the subscript, the understood subscript of 1 next to the magnesium. That means in 1 mole of formula units of magnesium hydroxide, you will have 1 mole of magnesium atoms. The 2 will distribute through here, so you will have 2 moles of oxygen atoms, and you will have 2 moles of hydrogen atoms. For aluminum sulfate, 1 mole of aluminum sulfate, you will have 2 moles of aluminum atoms, 3 moles of sulfur atoms, because the 3 distributes, and 12 moles of oxygen atoms. In the molecule of glucose, if you have 1 mole of glucose molecules, you will have 6 moles of carbon atoms, 12 moles of hydrogen atoms, and 6 moles of oxygen atoms. The takeaway from this is that in a chemical formula, subscripts represent a mole ratio of atoms in the compound. So, for example, there is a ratio for every 6 carbon atoms, there will be, or 6 moles of carbons, you'll have 12 moles of hydrogens and 6 moles of oxygens. Of course, that reduces down to a 1 to 2 to 1 mole ratio. All right, so let's now talk about what we mean when we say empirical formulas and molecular formulas. We're going to start by doing examples and seeing if you can determine what the difference between these two terms by seeing the examples. If we have a molecular formula of SO2, the empirical formula is also going to be SO2. If we have a molecular formula of H2O2, we're going to have an empirical formula of HO, 1-to-1 ratio. If we have a molecular formula of C6H12O6, the empirical formula will be CH2O, a 1 to 2 to 1 ratio. If we have a molecular formula of CH4, the empirical formula will be CH4. Note that all of these compounds are all nonmetals, making these covalent type of molecules. They all have covalent bonds. Okay, these are all nonmetals. That's how we know that. If we take a look at this set of chemical formulas, you'll see that we have a metal, nonmetal, metal, nonmetal, metal, nonmetals, metal, nonmetals. So this is ionic compounds, and we have a metal, nonmetal combo. So if we have a molecular formula of NaCl, the empirical formula is NaCl. Molecular formula of MgBr2 has an empirical formula of MgBr2. Molecular formula of K2SO4 has an empirical formula of K2SO4. And a molecular formula of Ca3PO42 has an empirical formula of Ca3PO42. So let's see what our takeaways are from having just done this exercise. I'm going to flip the page and go to the next page of notes. Okay, so our empirical formula takeaways is that an empirical formula is the lowest whole number subscript ratio. Another way to think about it is that an empirical formula is the lowest mole ratio of elements in a compound, since the subscripts represent a mole ratio. The molecular formula takeaways is this is the molecular formula that represents the actual number of atoms of each element in a compound. And the molecular formula can be the same as the empirical formula, but it may not be. If the molecular formula is different, it will always be a whole number multiple of the empirical formula. Okay, that's going to be an important thing to note as we progress through this topic. So what's interesting to notice about ionic formulas, if you go back and look at our examples of the ionic compounds, the molecular formulas were always the same as the empirical formula. That's an asterisk. What's interesting to note about covalent compounds is covalent formulas may be the same as the empirical formula, but they also may not be. Okay, so for covalent formulas, the actual molecular formula sometimes is the empirical formula and sometimes it is not. All right, so now that we know that an empirical formula is the lowest ratio of atoms in a compound, which may or may not be the molecular formula, we are going to use this idea that the empirical formula is the lowest mole ratio to help us figure out what the empirical formula is going to be. So we do need to remember empirical formulas are mole ratios, and those subscripts represent a mole ratio. So if I give you masses of each element, and you are being asked to figure out the empirical formula, for example, a compound is decomposed to find 0.96 grams of magnesium and 2.84 grams of chlorine. What is the empirical formula of this compound? Right? So we're given the mass of magnesium and we're given the mass of chlorine. Those are two different elements. We have masses of two different elements. We need to figure out the empirical formula of the compound. So the first thing to do is convert each element's mass into moles. So I'm going to set up a line here for magnesium and a line here for chlorine. Magnesium's mass was 0.96 grams. Set up a conversion fraction because we're going to convert this to moles, so grams will cancel, moles will go in the numerator. 1 mole of magnesium from the periodic table is 24.3 grams. And when I do this math in the calculator, right, if I do 0.96 divided by 24.3, I am going to get a very small number. I'm going to round it to two significant figures because of this original measurement here. So I'm looking at 0.040. 0.040 moles. Okay, we're going to do the same process for the chlorine. We've got 2.84 grams of chlorine. 1 mole of chlorine from the periodic table weighs 35.5 grams. Doing that math, we've got 2.84 divided by 35.5. And we get, we're going to go to 3 sig figs here, 0.0800 moles. All right, so what we've done is we've taken the masses of each element and we've converted them to moles of each. Once we have moles of each, we're going to determine the mole ratio, which means we're going to divide each mole quantity by the smaller of the mole quantities. So the smaller mole quantity belongs to magnesium. So if I start with magnesium, I'm going to take the moles of magnesium, 0.040 moles, and I'm going to divide it by that same number because that was the smaller of the two. Okay. The result of that is the number 1, right? Anything over itself is 1. Let's do the same for oxygen, right? Oxygen, we've got 0.0800. We're going to divide that by the smaller number, 0.40 moles. And we're going to see that that factors out to 2. So what we are seeing here is that when we convert the masses of each element into moles, and then we divide each mole quantity by the smaller of those mole quantities, we should get a whole number ratio of each element. That ratio will become the subscripts of the chemical formula, because remember, subscripts are a mole ratio. So we would write this formula as Mg, put them together, Mg, there's an understood 1 here, so I don't have to actually write it, but the subscript of 2. I just realized this is not O. This is chlorine. Okay, we're going to capture this. I still did the math right. This is chlorine, and then I started talking about oxygen. So my apologies. Okay. That doesn't make sense. So this is not MgO at all. This is MgCl. All right. Let's wake up. Get some coffee going. Okay, so there we go. There is our empirical formula. This is where paying attention to details and labeling your work, super important. All right, but we recovered and we're all good. All right, let's take a look at another example. Here's another example. If I give masses of each element, here we have a compound is decomposed to find 1.08 grams of aluminum, 1.08 grams of aluminum, and 0.96 grams of oxygen. What is the empirical formula of the compound? Remember, the first step is to convert each element's mass into moles. So I have aluminum, and yes, I have oxygen. Haha, gotta pay attention this time. So the aluminum mass is 1.08 grams. I'm going to convert this into moles. 1 mole of aluminum from the periodic table is 27.0 grams. When I take this 1.08 and divide by 27, I get the number 0.04 moles. Oxygen, 0.96 grams of oxygen. 1 mole of oxygen from the periodic table is 16.0 grams. So 0.96 divided by 16, and I get 0.06 moles. Okay, so again, the first step is to take the grams and convert them into moles. Next, we're going to take the mole ratio. So for aluminum, to find the mole ratio, you divide both mole quantities by the smaller of the two. The smaller of the two is the aluminum. So the aluminum, I'm going to take 0.04, divide by 0.04, and for aluminum, I'm going to get a ratio of 1. For oxygen, okay, the mole quantity there was 0.06. I'm going to divide by the smaller of the two numbers, 0.04. And here we're going to see, if we take 0.06, divide by 0.04, we're going to see that that's 1.5. Okay, well, that is almost a whole number ratio, but not quite. So if the ratio is not a whole number, it is likely a 0.5 ratio, which is what we saw here. In this case, we just double the numbers. So 1 becomes 2 and 1.5 becomes 3. That is the whole number ratio that you will now use to write the chemical formula. You put the two element symbols together and bring down the appropriate subscripts next to each element. And there's your empirical formula. All right, so those first two problems you were given masses. In this next example, you're going to be given percentages of each element. So let's say you're asked to calculate the empirical formula of a compound that is 43.7% phosphorus and 56.3% oxygen. So in this case, we're just going to make a simple adjustment, and we're going to assume that you have a 100-gram sample. If you have a 100-gram sample, then you will have 43.7 grams of phosphorus, and you will have 56.3 grams of oxygen. Then the problem just becomes the same exact problem that we saw before. For phosphorus and for oxygen, we're going to start with the mass given, 43.7 grams. And we are going to convert that into moles. Phosphorus from the periodic table is, to the nearest tenth, is 31.0 grams. So 43.7 divided by 31. Let's see, we're going to have 1.41 moles of phosphorus. Oxygen, we have 56.3 grams. 1 mole of oxygen is 16.0 grams. So 56.3 divided by 16. And here I have, we'll call it 3.52 moles of oxygen. Okay, so again, percentages, I just changed the percentage to gram because you can make an assumption about the quantity that you have, and those two percentages would give you the same number of grams in that 100 gram sample. So from there, take the grams, convert them into moles, and now we have to do the mole ratio again. So we're going to take both mole quantities and divide them by the smaller of the two. So for phosphorus, it's the smaller mole quantity, so 1.41 divided by 1.41. That's going to give us a ratio of 1. So you're going to see that you're always going to have this mole ratio. One of your elements will always be over itself and have a ratio of 1. Oxygen, if we take 3.52 and divide by 1.41, let's see, I've already got that number in my calculator, but I'll take the rounded number, 3.52, divide by 1.41, and we see that we get 2.49. So that's pretty close to 2.5. So we're going to call that close enough. And because this is a 0.5, we're going to double each one of these. So it's going to be 2 and 5. So writing the empirical formula, put the two element symbols together, P2O5. There's our empirical formula. Okay. Moving on to talking about calculating molecular formulas, right? So empirical formulas are always the lowest mole ratio of elements in a compound. It may or may not be the molecular formula. So this is the next step to figuring out what the molecular formula is. Okay, and typically these are separate problems. You're not typically asked to do both at the same time. So once you know the empirical formula of a compound, and you are given the mass of the molecular formula, you can determine the actual molecular formula by doing a simple calculation. You take the mass of the molecular formula, right? That's typically given. And you divide that by the mass of the empirical formula. And you may have to do, add it up from the masses on the periodic table. But when you divide the mass of the molecular formula divided by the mass of the empirical formula, you're going to get a multiplier. Okay, you're going to get a multiplier. If the multiplier is 1, then the molecular formula is the same as the empirical formula. If the multiplier is 2, then the molecular formula is, you will double the subscripts of the empirical formula. If the multiplier is 3, you will triple the subscripts of the empirical formula, etc. All right, so let's try some examples. Determine the molecular formula of a compound that has an empirical formula of NH2 and a formula mass of 32.06. Formula mass is the same thing as the molecular formula. Okay, so what we have to do, if we recall, we're taking the mass of the molecular formula, that's given, so that's going to be our numerator, so 32.06. And we're going to divide that by the mass of the empirical formula. The empirical formula is given to us, but not the mass. Okay, but the mass is easily figured out from the periodic table. 1 nitrogen at 14 grams 2 nitrogens at 1.01, add that up, and you are going to get 16.01. Okay. So if we then take 32.06, divide by 16.01, if we look in our calculator, 32.06 divided by 16.01, you're going to see that we get very close to a whole number of 2. So that's our multiplier. And what we then do is we take that empirical formula of NH2, and since our multiplier is 2, we're going to then double both of those subscripts. So this then becomes N2H4. That is our molecular formula. Let's take a look at one more example here. Determine the molecular formula of a compound with an empirical formula of CH and a molar mass of 78.110. So molar mass, this is basically they are telling us that this is our molecular formula mass. Right? So you take the molecular formula mass of 78.110, right? That's what goes on top. Then you have to take the empirical formula, figure out what the mass of that empirical formula would be. We have 1 carbon whose mass is 12. We've got 1 hydrogen whose mass is 1.01. We add those up and we're going to get 13.01. Divide to get your multiplier, 78.110. Divide by 13.01. And pretty much we get the whole number 6. So our multiplier is 6. So our empirical formula of CH becomes, because that's really a 1-to-1 ratio, we're going to multiply those subscripts by the multiplier of 6. So our molecular formula becomes C6H6. And there you have it. So what we have done in this video lecture is we have learned what an empirical formula and a molecular formula is. We've learned how to calculate empirical formulas from given masses or given percentages of the elements in that compound. And then we've learned how to determine the actual molecular formula when we are given an empirical formula and the mass of the molecular formula. All right, let me know if you have any questions, and I'll see you back in the classroom.